Hi, everybody. We'll continue with chapter 2, and this section is 2.5, the continuity of a function which we'll be using for limits. And continuity, the simple way before we dive into it is to, a function is continuous if it doesn't have a break. And if you draw it, you're not lifting the pencil or the pen from the canvas or the paper, and you continue. You have to do that. So no breaks, and you don't have to carry the pen or pencil out of the paper and put it somewhere else to draw. And we'll look at it. So I'll go ahead, switch the screen, and I'll do many examples on this. So a simple way that we talked about limit, of course, is that direct substitution. If it's defined in it, we say that the function f is continuous at a number a if the limit of f of x equal f of a. So there are three conditions we're going to look into. Then we're going to use other theorems. So number one, f of a is defined. The second is the limit of f of x as x approaches a exists. And the third is the limit of f of x as x approaches a equal f of a. So if this definition says that f is continuous at a if f of x approaches f of a as x approaches a, all right? So these three things, and we do some examples on it, right? And you'll see why. Right. There's some more information that I mentioned, and geometrically, this is what I talked about it, is continuous at every number if over an interval as a function whose graph has no break, and if the graph can be drawn without removing your pen on the paper. So let's look at this example. So for example, here, for 1, if a and is 1, then it's not defined there, right? So it's not continuous. For 3, you're drawing here, you get here, and you have to jump to start this way, so that's not continuous. And here you see it's the limit here is something else. So the third condition is not met. So f of 1 is not defined, this one here. And for the second one, it does not exist because of that jump. And of course, for 5, the limit of the function and f of 5 are different, right? Because the limit, as we mentioned, it's there, but f of 5 is this value here. Right. So this shows you 3 different kinds where the 3 things are not met. So where are each of the following functions discontinuous? Of course, if you have a rational expression, the first thing you want to do, see if it's in simplified form. So this one will be discontinuous at x equal 2 because there is a vertical asymptote there. So if we factor this, we're going to have -2 plus 1. All right, and so this is going to be some type of a line with having a hole at x equal 2. So it's discontinuous at that number. This function here is defined, f of x, when x equals 0, it's defined, it's 1. However, when you do the limit, that's not going to work with 1 over x. As x approaches 0, that's going to be different. And with this x square, there is a symmetry. I'll show the graph. So 0 for that one. And this one, it's similarly, it's defined, as f of 2 is 1, right? But you have here, if you do this similarly to A, so let's show it here. You see the limit is not going to be, of course, the same as f of 2. And here, 2 plus 1 will be 3 when you simplify this. So when you have x plus 1 here and x minus 2 here over x minus 2, and you cancel out, you get x plus 1. So the 2 plus 1 will be 3. However, f of 2 is 1. So, so let's go through the details. So f of 2 for A is not defined because there is a vertical asymptote. F of 0 is 1, but the limit, of course, and I'll show the graph, does not exist. The limit does not exist there because it's 1 over x, 1 over 0. There is a vertical asymptote as well there. And for this one, similarly, right, when you use the number 2 for the limit, you get 3. However, f of 2 is defined as 1. So that condition is not met. And here is the graphs to give you some understanding to what's going on. So you see here there is a jump or there is a hole in the graph. Here there is, it's defined there, but the problem is the limit does not exist there. All right, and this one, what else? For this one, you see we defined it there, but when you do the limit, you're going to this value here, 3, right? So the limit for the function as x approaches 2, it's going to be 3. However, f of 2 is 1. And by definition, it's continuous if that limit equals f of 2. All right. So let's look again at this example here. So the limit of this does not exist, right? You can still, some people would say, well, it is infinity and this and that because it goes up. Some people argue about that, but infinity is not a value or a real number. So it's going upward on both sides. However, it's not defined there. And it is discontinuous at 0, all right? And that's clear. And of course, but it's defined at that point there. And okay, so I think hopefully this helps you to understand what that continuity means. And you know, we use 3 conditions that should be there for it to be considered continuous. And there is something that's called removable discontinuity, which means you can fix the function so it's continuous. And we'll talk about the example. And for example, here in A and C, right? So here, there is a hole in the graph, but you can define this one. You can say, for example, well, f of 2 is 1. If you do this, then you fixed, you know, you defined it to fix it. So sometimes it can be fixed. And part C, yeah, part C, similar thing. All right. And part B is called infinite discontinuity, of course. Infinite discontinuity because it's going to infinity there. So a function f is continuous from the right, just like we defined in general continuous. If you have the limit of f of x as x approaches a, it's f of a. Here, of course, from the right, if that's satisfied, from the left, if it's satisfied. So a function, by definition, is continuous on interval if it is continuous on every number in the interval, right? So that's clear. So if it has to be continuous on the interval. Then some would use these type of definitions here. These properties, if f and g are continuous at a and c, are constants, these numbers here are constants, then the following functions are also continuous. So if f and g are continuous, then their sum, their product, their difference, their quotients, of course, with g of a cannot be 0, or a multiple c number times f are also continuous. So that's a helpful theorem there. So the functions, just what I mentioned, for theorem 5, any polynomial is continuous everywhere. That is, it is continuous on negative. So polynomials, like parabola, something like this, the cube, it goes this way. Actually, the cube goes something like this. You see, these are all continuous over negative infinity to infinity. Any rational function is continuous wherever it is defined. So rational functions, for example, if we do this way, it's defined here, it's continuous there. It's defined here, it's continuous there. So these are some to know. And there's some examples. And of course, for the cosine and sine, they are all continuous. So let's summarize. Of course, like tangent is not continuous when cosine of x equals 0, because the denominator here. So, and then you ask when that happened. So this is a graph that everybody needs to know, that as at pi over 2, there is that vertical asymptote. So this is a common used value. And of course, the period is pi. So if you take pi over 2 plus pi, and you do a common denominator, that gives you the next one. You subtract pi, you get the next one. And look at it here from the plus, it's going to negative infinity. And from the minus, it's going to positive infinity. So this is a picture that you all should know. Polynomials, trig functions, exponential functions, rational functions, of course, where they're defined, root functions, inverse trig functions, logarithmic functions. They are continuous on every number in their domains. If the point is in the domain, it is continuous there. All right. So for like this graph, for example, right, in this open interval, right, it's continuous, right? That function is continuous, so that's what it means. Also, the composition is also interesting. If this circle here is a composition, if G is continuous at A and F is continuous at G of A, then the composite function, F composed with G, is which means also substitution. So if, as a review from trig and algebra, F composed with G means in order, G is substituted into F. Right, so if you have also here, that's also in order, right? so is also continuous at A. So if G is continuous at A and F is continuous at G of A, so if we use A here, right, then it is continuous at A, the composition. An important property of continuous functions is expressed by the following. So we won't be dealing with the proofs, but it's a theorem that is correct. The intermediate value theorem is also interesting, and it helps in solving or finding the zeros, for example, or the roots. So, and this will help the graph with it. Then I'll do some example. So suppose that F is continuous on the closed interval AB. Let N be any number. So look at FA, FB. So for FB, FA. So something like this, where of course F of B and F of A are different. Then there exists a C value, something here, right? So I'll show the graph, but just so you start picturing what it is. Then there exists a C value in AB such that F of C equal N. So here is some pictures. So here is F of A, here is F of B, here is the interval AB. So if N is between A and F of A and F of B, then it will project on the graph, and there is some C such that F of C equal N. And look at it as well here. There is C1, there is C2, there is C3, but the point it's continuous. If it's in between these, it must capture. If you pick an N in between these two, then it has its value there on the x-axis. Right, another picture to it. F of A, F of B. If F of A is higher than F of B, and there is N, then it's kind of decreasing. And as you see, and you can project this too. All right. So so here is some example for it. So -1, 3, and and this one -3 to 3, and it crosses the x-axis between 1 and 2. All right. So as you keep zooming in, you can find the value there. In fact, the intermediate value theorem plays a role in very way. Here, the talk is about the computer, but we'll explain where it's useful for us. But here that the computers use this intermediate value theorem between consecutive points to calculate a finite number of points, right? But we'll do the examples and explain this intermediate value theorem. It's not that bad. So let's look at some examples. And this is from, of course, 2.5. So we need discontinuous, but continuous from the right at 4. Discontinuous at 4 means, you know, for example, this graph, it's discontinuous at 4, but it is continuous from the right of 4, which means it's defined. When we say the limit of f of x as x approaches 4, you know, the right-hand side, it has to be defined. It's f of 4. That's why this one here is solid. All right, so when you get this type of questions, the correct graph, you know, has to do with this. So continuous from the right at 4, so it is defined from the right at 4. Here it's not defined from the left. So removable discontinuity at 3, which means you need this dot here to be defined at 3. If you want to remove it or be able to remove it, you have to have it first defined. So we defined it at here by this dot. And jump discontinuity. Jump means just like we have at 5 here. It's not only discontinuous, but there is a jump. So we get here, but from the left, the limit is this number. Then to continue, from the right, you have to jump here to this value here. All right. So these are not bad. So let's suppose that f and g are continuous functions such that g of 6 is 3 and the limit of 3 f of x plus f of x g of x as x approaches 6 equal 18. Find f of 6. Well, this can be done maybe different ways, but one of them is, let's look at, we're given this whole thing, and we're given g of 6. So we have f of x and f of x here. So we can factor out f of x. Then you get 3 plus g of x. This is one way. Equal 18. All right. Then this is going to be the limit of 3 plus g of x here, which is, if you use those laws of limits, all right. And this is g of 6, which is here, a direct substitution. G of 6 is going to be 3. All right. This one here. So that one is just going to be 3, right? Because there is no, whatever happened is going to stay the same, right? All right. And this is 6, which we can, so it's 6 limit f of x. So I think there are different ways to do this, and this is one of them. 18 divided by 6, which is 3. And so maybe we can just continue it here and say the limit of f of x as x approaches 6 is 3. What does that mean? It means that f of 6 with that substitution is going to be 3. All right, so when you use that with that substitution, it equals to 3. Okay. Okay, so I put these numbers. So for 5, consider the following. So this function is defined from when x is less than 1, it's defined as this exponential function. And when x is greater than 1, it's defined as x squared. Right, so a here is 1. Find the left-hand side and right-hand side limits at the given value of a. So the limit of f of x as x approaches a, left-hand side, because a is given as 1. Well, it's the limit from the left-hand side is going to be x, which is e to 1, which is e. All right. So the limit of x, the right-hand side, limit of x to 1 from the right-hand side now is x squared. It's just 1 squared, which is 1. As you see, these the left-hand side and right-hand side are not equal. So conclusion, the limit does not exist at 1. And of course, you can graph and see what's going on and make sure from the left-hand side is solid, and from the right-hand side is solid, and from the left-hand side is not. So, you know, your x is has this as the asymptote. This is 1, so it's going to go something like this. Then not solid there for 1. Then x squared. You know, if you try to just to graph, you know, what this means is just you graph it on this side, right? So it's going to be x squared, whatever you plug in the values. So y equal x squared and y equal ex, and you see that it does not exist. How would you remove this discontinuity here? Of course, rational function here, we need to first look at it. Two numbers multiply -5, and this is negative, so -5 and +3. And so x plus 3. Right. And so that's one way, you know, that's how we would kind of figure out this thing. So if we use here f of 5 for this here, 5 plus 3 would be 8. So we can redefine it this way. F of x is x squared minus 2x minus 15 over x minus 5 when x, so let's do that part in a minute. When x equal to 5, so when x equal to 5, the value is 8, and when it does not equal to 5, the function is that way. But I think for you, maybe for the homework, you're just going to put this value in. So find the values of a and b that make f continuous everywhere. So this is a summary. This is the goal. If we understand everything happening up to now, we need to apply it here. This is a type of a classical problem to build the understanding. Do we understand that the limit, the left-hand side and the right-hand side have to be equal for, you know, for this limit to exist and stuff? So let's look at this example. Find the values, and this is number 9. Find the values of A and B that make F continuous everywhere. So if it has to be continuous everywhere, you see, when we get to these points, this is a polynomial. It should be no problem. And this one here, so we just need to make sure that they're defined. This x minus 2, you know, it breaks at x minus 2, but we need to make sure that it is defined at x equal 2, right? So that's a few things. If we can connect these 3 pieces, then we will, so we will find the values of A and B that will make this function continuous everywhere. So let's look at it this way. The limit, so this is x is less than 2, so like this way. So the limit of x squared minus 4 or x minus 2 as x approaches this, right, equal x, this factors and now if we use the direct substitution is 4. So the left hand side limit for this value of 2 is 4. We want the right hand side value at 2 to be also 4. So the limit you see this, you can use that direct substitution here, which means a 2 squared is 4, a 2 and a 3. So for a minus 2b plus 3, we want this to be 4. All right. All right. If this is 4, that means 4a minus 2b equal 4 minus 3 is 1. So that's one equation. Let's call it stop. So now the next issue is this 3. We want to make sure that, you know, from the left side of 3, you know, we're not getting 10, and the right side of 3, we're getting 15, right? That's what we need to do. So the left for 3, it's ax squared minus bx plus 3. This one also is direct substitution. So 9a, 3b plus 3. And now from the right side, it's 2x minus a plus b. And that would be 6 minus a plus b. And we want these two to equal. So 9a minus 3b plus 3 equals 6 minus a plus b. So 9a, if we add a, we get 10a. Negative 3b, and you subtract b both sides, negative 4b. And 6 minus 3 will be 3. All right, and now the second equation we got is 2. So anytime you have 2 unknowns, A and B, you need 2 equations to find them. We can use substitution or elimination. It looks like, you know, you have a bunch of numbers, so let's use elimination. By having 4a minus 2b equal 1, 10a minus 4b equal 3. let's say I want to cancel the b here variable. So if I multiply this by 2, I should get 4b, right? We'll get negative 4b, so that won't work. Let's multiply by negative 2, so we get plus 4b. So plus 4b minus 4b, okay. So the star and the 2 stars. So now the star becomes negative 8a plus 4b. Don't forget this part here. And the 2 stars, I didn't do anything to it. You can also eliminate a if you want to, whichever is easier. Negative 8 plus 10 is a 2a. This is out. And negative 2 all right, 1. So a is half. And we can pick either a, so from star, for a, either star or 2 stars, either way. So if we do this, then you want b by itself, you're going to bring 2b to this side and bring 1 to this side, subtract 1. So something like 4a minus 1 equal 2b, and you will divide by 2 both sides to get b by itself. All right, so we need to do this. A is 1/2. 1/2 times 4 is 2. 2 minus 1 is 1, so b is 1/2. All right, so this problem 9, practices a way to better understand this thing. So this function can be continuous everywhere if the limit for these parts, here the 2 and the 3, the left-hand side and the right-hand side are equal. So that's what we base this method on. We find the left-hand side, right-hand side, we equal them, find the first equation, then we go to number 3 there, we do left-hand side, right-hand side, we equal them, and we find the second equation. And we use something from algebra to solve by elimination. And we find that a is 1/2 and b is 1/2. So we can rewrite this by putting the halves there. And that's going to be a function that is continuous everywhere. This problem, I put it as just to explain the intermediate value theorem, to show the root, which means also a 0 or an x-intercept there. So this function is continuous on the interval 1, 2. If f of 1 is negative 3 and f of 2 is 13, all right. Just to give you some picture, negative 3, 13. So since 0 is between this negative 3 and 13, then there is a c number here between 1 and 2, such that f of c is 0 by this intermediate value theorem. So there is an equation in the interval 1, 2. But the way to really, if we want to simplify this, let's say if you want to simplify it, what do we need to know? If you get f of 1 negative, right? So f of 1 negative, let's say this value negative, right? So the y value of 1 is negative. then f of 2 is positive, the y value of 2 is positive. There is no way this thing is going to go from negative to positive without crossing the x-axis. So that's the way that's probably not explained in this section about this. So there is no way for it to cross it, to pass without crossing it. So it must cross it. And if it crosses it, then there is a root there, or a zero, or we call a zero. All right. So there is a root for the equation in the interval. So if you, so the note, so AB, right? If f of A times f of B, you know, negative 3 times 13 is negative. If you multiply this by this, is negative, then there must be a root there. So that's a nicer way of talking about this intermediate value theorem. All right, so we'll close with this example, which we go back to this continuity with the operations, but this is not an operation as addition, subtraction, multiplication, division. As you see, there is a function there, x to 6, inside another function of sine of x, right? So x to the 6th is continuous function, right? It's a polynomial. And sine of x is also continuous function, right? So this is a continuous function over R. And this is continuous function over R. So they all, so here there is no issue, they're both continuous. All right, so the function now, again, this is a composition. So we have a function, you can call f of x as 1 plus cosine of x. This one is continuous. Cosine of x is just, you know, the graph, it bounces between -1 and 1, then now we add 1 to it. It's still continuous over the x-axis. And the logarithmic function, it's also continuous over its domain, right? But its domain is positive values, right? Continuous over its domain. So what's the issue that happens? We know the log, if you do on your calculator, you know, log of 0, what would log of 0 be? You know, what is log of 0, right? It's going to be, it's undefined. So the issue here is anytime 1 plus cosine of x equals 0, this function is undefined. So this means cosine of x equals -1. And if you look at the unit circle, cosine of x equals -1 at pi, right? Which means whether we're going positive pi or negative pi, all right? So every other cycle, anytime, because it's periodic, and if you add another 2 pi or you subtract another 2 pi, then same thing happens. Which means it's not continuous at these values. So it is discontinuous at these odd multiples of pi, all right? I think that's it for this section. If there are other examples, we'll solve them in class. All right, thank you.